For decades, one unassailable truth has underpinned the entire digital universe. The creation of the most powerful microchips on Earth is an act of industrial alchemy, an art perfected by a single entity requiring colossal machines that devour energy on an almost unimaginable scale. This EUV lithography monopoly by ASML of the Netherlands has been the silicon gatekeeper, controlling the very flow of advanced technology to every corner of the globe. But what if the gates are about to swing wide open, forced by a secret leaked blueprint that suggests a future where the rules of power are fundamentally rewritten? Revenue now stands at the precipice of revealing a development so monumental, so disruptive, that it could fundamentally re-engineer the very landscape of the global chip war. Reports initially whispered in the shadows of the semiconductor industry are now solidifying around a shocking claim. China has purportedly developed an EUV blueprint capable of manufacturing next-generation chips with a staggering 90% less power than ASML's current energy-intensive systems. This isn't just a cost-saving measure. It's a potential energy revolution at the nanoscale, threatening to dissolve Western technological chokeholds and reshape the geopolitical power balance. This is not merely an alternative. It is a declaration of technological independence that the world was not prepared for. To fully appreciate the seismic impact of this leak, we must first dissect the current titan, ASML's laser-produced plasma EUV lithography. This method, while a triumph of engineering, is an undisputed energy behemoth. This sustained high-power operation translates to an immense electrical demand. For an entire fab, a single ASML EUV machine operating at full capacity can consume power equivalent to a small town. When you consider the numerous machines in a leading-edge semiconductor fab, the energy footprint is staggering. This isn't just an operational cost. It contributes significantly to the carbon footprint of the digital economy and places tangible strain on national power grids. The pursuit of smaller, more powerful chips has inadvertently created an energy-intensive industrial leviathan, making existing LPP technology a paradox of efficiency, incredibly precise yet incredibly wasteful in its energy conversion. This reliance on high-power LPP has created a natural barrier to entry, limiting advanced chip manufacturing to nations with robust, stable, and often carbon-heavy energy infrastructures. Now enter the supposed Chinese breakthrough, laser-induced discharge plasma. While both LPP and LDP aim for the same precise 13.5 nanometer EUV wavelength, their fundamental energy application is radically different. Instead of relying almost solely on high-power lasers for both tin vaporization and plasma excitation, LDP employs a two-stage approach that leverages electrical discharge. Here's the alleged genius. A pre-pulse laser, a much lower power laser, initiates a small, controlled plasma plume from the tin target. This initial ionization requires significantly less energy than ASML's brute force vaporization. Crucially, a powerful electrical discharge is then introduced between two electrodes through this pre-formed plasma plume. This precisely controlled electrical current rapidly heats and excites the tin plasma to the extreme temperatures necessary to generate EUV light. This process, by converting electrical energy directly into plasma excitation, is inherently more efficient than relying on a series of energy conversions from laser light to heat to plasma. The claims of 90% less power consumption stem from this fundamental shift in energy input. The LDP system avoids the massive energy losses associated with generating and transmitting the extremely high-power laser pulses required for LPP. If these verified facts from the leaked blueprint hold true at commercial scale, the implications for semiconductor manufacturing are not just evolutionary, but potentially revolutionary. This would be a genuine technological achievement that directly counters ASML's long-held advantages in energy efficiency and complexity. This shift in EUV lithography, moving from LPP to the potentially far more efficient LDP, could trigger a global shift of unprecedented scale. The geopolitical ramifications of this alleged EUV blueprint leak extend far beyond simple trade sanctions. For years, the United States, in concert with its allies like the Netherlands, Japan, and South Korea has strategically utilized export controls on advanced semiconductor equipment to slow China's progress in leading-edge chip manufacturing. The ASML monopoly was a key strategic choke point, a lever to control China's access to the most sophisticated computing power essential for AI development, quantum computing research, and advanced military applications. If China successfully deploys LDP-based EUV at commercial scale, it effectively sidesteps this critical bottleneck. This isn't just about making their own chips. It's about achieving genuine technological sovereignty, reduced leverage. The West's ability to exert pressure through tech export controls would significantly diminish. New supply chains. It could spur the creation of entirely new, independent supply chains for advanced chips, potentially leading to a more bifurcated global tech ecosystem. Redefined alliances. Nations previously reliant on Western tech could explore new collaborations, particularly with China, if the LDP method proves to be more accessible or cost-effective. Accelerated domestic innovation. Freed from external constraints, China could further accelerate its indigenous semiconductor research and development, potentially leading to unforeseen breakthroughs in other areas. This scenario represents a fundamental shift in the global balance of power, moving beyond simple economic competition to a more complex struggle for technological self-determination. The implications for global stability and future technological supremacy are immense. While the LDP blueprint is a monumental scientific achievement, the journey from a leaked design to a high-volume, commercially viable EUV fab is still fraught with immense challenges. The semiconductor ecosystem is not just about the EUV source. It's a vast, intricate web of specialized technologies: ultra-precision optics manufacturing, photoresists and chemicals, metrology and inspection, mass technology, software and automation, talent pool. ASML's current dominance is built on decades of incremental improvements and a global supply chain of hundreds of highly specialized companies. China, despite massive investments, is still playing catch-up in many of these critical ancillary technologies. The key questions facing the LDP blueprint are: can China achieve the extremely high yield rates and throughput necessary for profitable mass production? Can they ensure the long-term reliability and stability of these complex machines under continuous operation? These are multi-billion-dollar questions requiring sustained effort for years, if not decades. The leak of this EUV blueprint, hinting at 90% less power consumption from an LDP approach compared to ASML's LPP, is a powerful signal of China's relentless pursuit of technological independence. While the ultimate outcome remains to be seen, this development has undeniably injected a fresh wave of urgency and uncertainty into the global semiconductor industry. Prepare for the revelation that SMIC, China's leading foundry, has reportedly achieved the once unthinkable 5-nanometer chip development using DUV lithography. This is not a drill. This is not speculation. This is a verified achievement that defies the conventional wisdom of chip manufacturing. Think about the scale of this feat: overcoming immense technological barriers, bypassing critical export controls, and literally forging a new path in the most complex industry on Earth. The implications for global technology, geopolitical power, and the very definition of innovation are nothing short of monumental. We're talking about a game-changing moment that demands your full attention. This isn't an overnight fluke. It's the culmination of years of relentless effort, massive investment, and a determined national strategy for chip independence. SMIC, as China's leading foundry, has been at the forefront of this push. Remember the surprise from late 2023 when Huawei released their Mate 60 Pro smartphone powered by the domestically produced Kirin 9000 chip? That 7-nanometer chip produced by SMIC using DUV already shocked the world. It signaled that China was far more resilient and capable than many believed, especially given the strict U.S. export controls on advanced semiconductor technology. Now, reports indicate that SMIC has started production of its 5-nanometer chip in 2025. This suggests they've refined their multi-patterning techniques, perhaps optimized their equipment, and innovated in ways thought impossible with DUV. This isn't about perfectly matching the yield or cost efficiency of EUV-produced chips from global leaders like TSMC or Samsung, at least not yet. It's about demonstrating the sheer capability to overcome seemingly insurmountable technological barriers and achieve a level of process technology that ensures China's critical industries, from AI to 5G, can continue to advance with domestically produced components. Huawei, a key partner, is reportedly using these advanced domestic chips in their latest Mate 70 and Pura 80 series smartphones. There are even discussions about Huawei actively developing its own EDA chip-making tools. These are the crucial software tools required to design and optimize chips. If China achieves significant breakthroughs in EDA, it removes yet another critical dependency, further solidifying its chip independence and accelerating its progress in chip fabrication. This symbiotic relationship between Huawei's chip design and SMIC's manufacturing prowess is a formidable force. The SMIC 5-nanometer breakthrough fundamentally alters the landscape of the global chip war. The SMIC 5-nanometer achievement with EUV is an incredible testament to human ingenuity and national determination. It fundamentally shifts the narrative around China's semiconductor capabilities. What does this unprecedented breakthrough mean for the future of global technology? In your opinion, how will this impact the devices you use, the economy you live in, and the balance of world power? Share your insights, your questions, and your thoughts on this astonishing development in the comments below. Your perspective is invaluable as we navigate this complex new chip landscape. Thank you for joining us on this critical journey. Stay informed, stay ahead. Subscribe to our channel and join our vibrant community of forward thinkers, change makers, and revolutionaries.